Number 3, f of x equals e to the x, enter that a equals to 2. You know the drill. Evaluate the function, or name the function e to the x, evaluate it at 2, e to the second power, take the first derivative, e to the x, evaluate f prime at 2, it's going to be the same. All I'm doing is just writing more prime symbols because the derivative of e to the x happens to be the same all the time. And the result of evaluating the function and their derivatives, it's not going to change at all. What changes is the version or the form of the power series representation that we will come up with. And well, e squared, and that's fine, that's enough. So let's recall our formula for the power series representation. So f of x equals to sigma n equals 0 to infinity, the nth derivative x minus a. This time, in the previous exercises we just used x to the n power. This time we're going to call x minus a because we have a different center, which is a to the n power over n factorial. And in particular, for our case, that's sigma n equals 0 to infinity. The nth, should be evaluated at a, these derivatives, alright? Forgot that part. Evaluated at a, x minus a, or not a, actually, in this case is 2. 2 to the n over n factorial. So let's go ahead and write the terms for this power series. So number 1, f of x equals f of 2 plus f prime of 2 times x minus 2 to the first power. Well, technically there has to be f of 2 x minus 2 to the 0 power over 0 factorial over 1 factorial plus f double prime of 2 x minus 2 to the second power over 2 factorial plus f triple prime evaluated at 2 x minus 2 to the second power over 3 factorial. But of course we're not going to write infinitely many terms. We can just use our dot 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 symbol here just to indicate infinity here in a way. Alright, well, let me just highlight what we will use. Essentially we have everything pretty much figured out. Yes.
So with that, F5
No, it's to the first power. Do you mean this n?
I'm asking about the 2 that you have right now.
This one.
Yeah, right there. That.
No, that's just f of 2, which is this f of 2.
Okay.
Yes.
And shouldn't it be x minus 2 cubed?
Yes, that's what I meant. Thank you. Let me make this a 3. Well, come on. Yeah, that's a 3. And well, so let's keep highlighting the factors that I need. E squared, it's going to be this f prime. This f double prime is this another e squared. This f triple prime, e squared. I mean, nothing changes as of that. Well, so number 1. F of x equals e squared. I'm going to leave this x minus 0 to the 0 power just so I can see a pattern. F double prime, which is also e squared, x minus 2 to the first over 1 factorial. I'm not going to evaluate the factorials again for the same reason, which is to find a pattern. E squared, x minus 2 cubed over 3 factorial. And well, our job right here is to just go about the sigma representation of the series.
For the first term, it is supposed to x minus 2.
X minus 2, yes. I don't know where the 0 came from. Thank you. So f of x equals sigma n equals 0 to infinity e squared x minus 2 to the nth power over n factorial. That's our pattern in this case because, well, the e to the second power is a common factor to all polynomial terms. And, well, what do we have? X minus 2 and in the factorial increasing in the same order as the nth term. 0, 1, 2, 3. So that should work. Now, if you ask me, do I like doing this using the general form? I mean, the Taylor series and Maclaurin series version. I mean, it's kind of tedious to take 3 derivatives, 4 derivatives, and actually, I mean, like getting all the same result in some cases, pretty much like for nothing, instead of getting something different all the time. So it looks like wordless. Well, it's not that it's wordless. In some situations, it can be hard. So what if we want to find power series for functions like this? F of x equals x to the 4th e to the 3x squared. G of x equals x squared cosine 9x. H of x equals this madness here. I can't even well, I can, but I just don't want to. Well, just think about evaluating at whatever center A or 0. It's no big deal. Just plug it in. Finding the first derivative, well, it's all right. Do the product rule. Okay. And however, by the second derivative and on, can you think of all the madness that we're going to get into finding or having to do a bunch of product rules, combining like terms to then evaluate them? Did you see the hell that awaits for us here? Well, lucky for us, we have formulas to get this done. So we're not going to do this a long way. So you might remember back from Calculus 1 when you took derivatives using the limit definition. That was kind of a painful process. Then they gave you what they call the shortcut rules, which are really called the differentiation rules, the general power rule, which you can use it to find the derivative within 2 or 3 seconds instead of doing the limit definition. So that's something similar. We get a power series, the long method, and the short method is just using a summary of power series. All right? And all this power series we already obtained using the long methods. We just got the power series for e to the u. Well, actually, let me mention something. Your textbook is not going to give you all this in terms of u. It's just going to give it to you in terms of x. I'm writing this, I typed this in terms of u, thinking of potential composite functions because, well, we will be asked to find the power series representation of e to the 3x, for example. And well, in this case, we can do like a u substitution, do the work in terms of u, and then go back substitute. And of course, so we already got a power series representation for the geometric one. We did the one for ln via integration of series. Remember that one? And we also did the sine, cosine, and arctangent via manipulation plus what else? Integration to get the arctangent function. So we're just going to use these forms to come up with power series. So in this case, instead of taking 4 derivatives, which is not that bad, it's just tedious, we're going to do the following. Okay, so let's start with the function f of x. That's highlighter. So that's f of x equals e to the 4x. Well, in this case, how about we turn this into an e to the u? So I'm going to call this e to the u, where u equals 4x. And well, we know a power series representation for e to the u, and that's just sigma n equals 0 to infinity, u to the n over n factorial, and that's it. Just make sure to denote that u equals to 4x, and just back substitute for u. Sigma n equals 0 to infinity, 4x to the n over n factorial. And we're essentially done with writing down the series in terms of x. However, we need to further simplify this by distributing the power over the 2 factors inside of the parentheses. And that is sigma n equals 0 to infinity, 4 to the n, x to the n over n factorial. Not even a single derivative. Not even the second, third, fourth, fifth, seventh, 19th derivative. Alright? Just using the formulas, shifting the u, set up a u, come up with a series, simplify. A minute or less, right? How long did that take? A minute or less. Alright. F of x equals 3 e to the 3x, but this time it's centered at x equals to 3. And be careful with this one. Although, yes, it looks, the process of just using the formulas for power series looks simple. Well, it depends whether we have the shifting already set for us. For this one, it's not set. For this one, it was centered at x equal to 0. That is a Maclaurin series, so we just use the plain vanilla series for x. In this case, this is not going to be a plain vanilla series. This is going to be a series centered, that is going to look like x minus 3 somehow. Now, the question is, do you see an x minus 3 shifting on the original function? It's not there. We have to do it ourselves. All right. F of x equals e to the 3 times, e to the 3x. Well, how do we turn that x into x minus 3? Well, we wish we had an x minus 3, and we can make our wish come true by, how about at 0? I mean, the number 0 can be represented by your favorite combination of numbers, negative 1 plus 1, negative 3 plus 3, negative 5 plus 5. So how about we use negative 3 plus 3 so it matches our shifting here. So I'm going to write this as e to the 3 times x minus 3 plus 3. And careful, because even though we have 3 terms right here, I'm gonna group it and treat this like we had 2 terms instead. That is, this is one term, the one that is going to give us the shifting, the desired shifting, and this other leftover term. This to distribute 3 times this quantity and 3 times that quantity. That's e to the 3 times x minus 3, and 3 times 3, isn't that a 9? So we already sort of have this 3 with this x minus 3. It doesn't matter if it has a coefficient. That's fine, don't worry. But I have an extra term, which is that plus 9. So in this case, what we're going to use is below sub exponents backwards. That is e to the 3 times x minus 9 times e to the 9th power.
The x minus 3.
That's what I meant. Thank you. Minus 3. All right. Well, in this case, this e to the 9 looks more like a coefficient, so I'm just going to rewrite the order of the factors. So in this case, e to the 9th, e to the 3 times x minus 3. And well, we have some e to the u where, well, just give this e to the 9, that's only a number. This is e to the u, where u equals to 3x minus 3. That means e to the 9th, sigma n equals 0 to infinity, u to the n over n factorial, because again we're using the general representation for an exponent, for the power series for an exponential function. But just make sure to denote that u equals to 3x minus 3. Just back substitute for u. This is e to the 9th power sigma n equals 0 to infinity. That's 3x minus 3 to the n power over n factorial. And we're essentially done coming up with a power series representation in terms of x with the desired shifting, that is x minus 3, because we want a series centered at 3. The only thing we need to do is just distribute the power on the 3 and the x minus 3 and introduce this constant factor inside. Sigma n equals 0 to infinity, e to the 9th power, 3 to the n, x minus 3 to the n over n factorial. Do you see all the amount of factors? E to the 9, 3 to the n. It looks like it would have been quite of a big task to figure out a pattern for the series had we done it instead using the long way, which is finding a number of derivatives and then having to figure out the pattern. So even though it was a little tricky to shift this to get the desired center of the series, but at least this is preferable over going the long way, trust me. Let's do another one. So we have a bunch with exponentials, then we're going to deal with others later, all right? For the next example, f of x equals x to the 4th power e to the 3x squared, but this time centered at 0. And again, just think about this function getting its power series representation using the long process. Envision all the amount of derivatives, all the work, product rules. How many product rules? I don't know. Many. Plus some chain rule here, a lot of simplifications, and just to evaluate this and get maybe 0 or 1 or, you know, weird things. Alright, so instead we're going to use the formulas, but the good thing in this case is center at 0. We don't have to shift anything. This x squared is the same as saying essentially x minus 0 squared, so we already have the function with the correct shifting which matches the center. So f of x equals x to the 4th e to the 3x squared. Well, we already have the elementary function. We're going to focus only on the exponential, so don't mind the x to the 4th power for now. That will be introduced into the series later. In the meantime, x to the 4th e to the u, where the u equals to 3x squared. And well, what do we have? E to the u, x to the 4th, sigma n equals 0 to infinity, u to the n over n factorial, where u equals 3x squared. And all we do is backs up. X to the 4th, sigma n equals 0 to infinity, 3x squared to the n power over n factorial. And I'm going to do a couple of things. I'm going to introduce this x to the 4th into the series. That is x to the 4th times, and in this case I'm going to distribute the power n to both factors, the 3 and the x squared. So number 1, this will be a 3 to the n, and here x squared to the n power, what do we have? We have the power of another power. What do we do with the powers? Multiply, right? 2n. And the whole thing over n factorial. But in this case, well, we have the same base. A base x, which is an x to the 4th power. And that's 3 to the n, x to the 2n plus 4 over n factorial. So just look at this power right here. So after doing all these derivatives and writing the Taylor polynomial, imagine having to figure out the pattern of powers 2n plus 4. That wouldn't have been an easy task. So that's why it's just great to have these formulas for power series representations instead. All right. Let's do another one. Now we're going to use a different function, x squared cosine of 9x. And this is centered at 0, which is great that it's centered at 0 because, I mean, otherwise for a trigonometric function centering at another value, it's going to be madness, all right? So number 1, f of x equals x squared cosine 9x. And well, we can identify our elementary function already, which in this case is cosine. That composition at 9x, we can call that our u. So that's x squared cosine of u, where u equals to 9x. Well, x squared sigma n equals 0 to infinity. Now we need to look for the power series representation for the cosine function, not anymore for the exponential function. Let's go back to the previous page and identify that one. And so cosine u, that series representation is an alternating series, u to the 2n over 2n factorial. Well, if you well, because you will be asked to memorize this power series representation, so I think a good bit here is to keep in mind that sine is an odd function, as mentioned before. in the last lecture, and cosine is an even function. So the fact that sine is an odd function contains odd powers and odd factorials in the denominator, and cosine is an even number, contains even powers and even factorials in the denominator. Alright? So let's just use it. Let's just use it. That's negative, oh come on, negative 1 to the n, u to the 2n over 2n factorial. And by the way, note, make sure to use parentheses around the 2n factorial, because 2n factorial is not the same as 2n, the whole thing being factorialized. Alright? So, and you can try it for different integers. In fact, I think this is only true for n equals 0. Try it for n equals to 1. Well, I think it's going to work for, no, it's not going to work for, yeah, I think it's going to work for n equals 1, but for larger numbers it's not going to work. So just make sure to have the parentheses around. And our u equals 9x. So this is 9x, and well, all we have to do, yes.
There's the x squared.
And that's supposed to be squared. Thank you. So just back substitute. At the same time, I'm going to introduce the x squared factor. That's going to be 9 to the 2n over 2n factorial. Okay. Number 1, let's distribute the power 2n to the 9 and to the x right here. N equals 0 to infinity. X squared, 9 to the 2n, x to the 2n over 2n factorial. So there's a couple of things to do right here. Number 1, that x squared, combine it with the x to the 2n to turn it into, I'm going to leave a space for something, you'll see, x to the 2n plus 2 over 2n factorial. And this 9 to the 2n can be further reduced or simplified to 9 squared, which is 81 to the n power. And starting at 0, going all the way to infinity. So imagine having to figure out this pattern of powers and this pattern of powers of 81 in our derivatives. It's simply going to take forever. Just one problem like this, the long way, would have taken at least the whole lecture to do. Instead, formulas are here to make our job easier. So there's one more, and then I'm going to make up a couple more examples, because well, this is the last one I typed on the PDF file. And well, so this one, f of x equals the one from the exam, from the definition box in the previous couple of pages. Just imagine having to do, number 1, a product rule that involves a chain rule here, an ln rule, another chain rule, and well, after getting the first derivative, that becomes some quotient because of the derivative of ln, which is 1 over its argument. So the second derivative would have involved a combination of product rules, chain rules, and also quotient rules. Thanks but no thanks. Alright, so formulas. And by the way, something I forgot to mention here, at x equals to 3. Alright? And this is just to match our shifting. If it were a different value, well, you don't want to do this for a different value. Alright? So, how about, well, let's write down the power series first, the function first. F of x. That's, what's this? Oh, x minus 3 to the 4th ln of 1 plus x minus 3 squared. And well, from here we don't need to do any shifting, we don't need to do anything weird. It's everything just ready to call for a u in this case. So that is x minus 3 to the 4th ln of 1 plus u, where u equals x minus 3 to the 2nd power. And now we can go about looking for a power series involving ln of 1 plus u. And we have one. So let's look for it. It's this one right here. Actually, we came up with something different when we did it. Using, what was that, the geometric series, the integration. But the thing is, this one is shifted, has a different shifting index, but it's essentially equivalent. So this one, be careful, because this series, in the form that is given, it starts at n equals to 1, not an n equals to 0 like the other series. So let's just use it. I'm going to write it down here. So that equals x minus 3 to the 4th ln, oh, not ln, that's already sigma, n equals, what's that, 1 to infinity, and that's a negative 1 to the n minus 1 u to the n over n, where our u is this madness here, x minus 3 to the 2nd power. And we're just ready to back substitute for this. Alright? So x minus 3 to the 4th sigma n equals 0 to infinity, negative 1 n minus to the n minus 1, that's x minus 3 squared to the 2nd, or not to the 2nd actually, that's to the n over n. And you know the drill for simplifying this. So raise the power, power of another power, and also introduce this x minus 3, because this x minus 3 is also this same x minus 3. And that's a negative 1 to the n minus 1, x minus 3 to the 4th power, x minus 3 to the power of another power, multiply the powers, and just combine them into a single base, because they're the same base. Just do whatever operation needed in the exponent. Yes?
Did you shift the index?
No, I think I got used to the n equals to 0, so yeah, thank you. So again, see? Yeah, 1. 1 to infinity, negative 1 to the n minus 1, x minus 3 to the 2n plus 4 over n. So again, just look at this result. Would you be able to figure out x minus 3 powers, or powers of 2n of the form 2n plus 4, on top of having to do a lot of product rules, chain rules, quotient rules? I mean, it's just not feasible to do this, alright? Well, so this is the last example I typed for the notes. Let me make up something else. I have one for which we do not have a power series representation for, and I'm going to do one that is a usual exam question. All right, so, well, what about f of x equals 2 to the x power at a equals to 0. To make it simple, let's just center it just center it at 0. All right. Well, so we don't have a power series representation for an exponential function whose base is different than e. We have one for e, but in this case, the trick here is to turn this exponential function base a into a function base e. And well, what's the trick? Well, there's something we need to recall from pre-calculus. That's the inverse properties between natural logs and exponential. Well, the inverse properties or composition properties, and those properties we use them to solve exponential equations and logarithmic equations. You know, like whenever a to the ln, whenever we have e to the ln, both cancel to give the x, or ln of e, they cancel to give the x. All right. However, we are going to use these properties backwards to turn that 2 to the x into an exponential function base e. Let me just box this. So, and in this case, I'm going to use the first property because, well, e to the ln of 2 to the x, you know, cancel e to the ln to get back to the 2 to the x. Alright? Well, and then from here, I'm going to use another property from precalculus. That's whenever we have an ln of a to the n, that's n ln of a. In other words, the power becomes a coefficient or the coefficient becomes a power, which is what we're going to do in the exponent of this e function here. Make that a coefficient. And well, this is e to the x times ln of 2. However, well, that ln of 2 looks more like a numerical factor. I will just reverse the order of the product here. And now we just turned that function, that exponential function base a, other than e, into that of an natural exponential function. And I think from here, we can already call e to the u, where u equals ln of 2 times x. And we know a power series for e to the u, which is sigma n equals 0 to infinity of u to the n over n factorial, where u still ln of 2 times x. And well, just back substitute for u, n equals 0 to infinity all to the n power over n factorial. Just raised both factors inside of the brackets. N equals 0 to infinity ln of 2 to the n x to the n over n factorial. And that's the power series representation for an exponential function whose base is not e. Now, well, we did this just for the function 2 to the x. What if we have instead 7 to the x, 5 to the x, 93 to the x? Well, you can generalize this result and just change the number in the logarithm. That's it. In general, a to the x, that'll be sigma n equals 0 to infinity ln of a to the n power x to the n over n factorial. Now, if you think of the exponential function, you know, the exponential function base e, you would do ln of e. But what's ln of e? 1 to the n? That's just going to leave us with x to the n over n factorial back again, right? So, but in this case, you have another form for an exponential function. I mean, in general form for an exponential function with a base other than e. Question?
So can I write the exponential of natural 2, the n over ln?
Which one? What line?
ln 2 over n power, and this means the n over natural.
N over the natural log? No, because that's actually not a logarithmic property. So we're just using the power to coefficient to.
Yeah, similar to how we write tangent of x squared. Tangent of x all together squared. We write the exponential right after tangent.
The exponential. Do you mean, okay? What part of the process are you referring to for this one?
Natural log.
Right here?
Yeah.
So, do you mean 1 over ln? But that'll leave us with negative exponents, and well, I don't see.
I'll help you out.
Yeah, okay, yeah. Let's do another one, and the next one, it's a very typical exam question. All right. F of x equals to. Okay, let me see what I did in the other in the other section. Give me 1 second. So I want to do the same exercise. Okay. Oh, come on, not the same document. Okay, so f of x, 7 over 5 plus x at a equals to 2. Alright, at a equals to 2. So, there's a couple of tricks that we need to. So number one, let me refer to the series 1 over 1 minus u equals to sigma u to the n and from 0 to infinity. So what do we need to do? So there's a couple of things that we want. Number one, well, the 1 in the numerator, well, it doesn't have to be a 1 all the time, because this coefficient 7, I can just write it outside and in the end just multiply it back. However, there is a situation with the denominator. This 5 right here has to be a 1 all the time, and this x has to be a negative in the front. So number one, I'm going to do the shifting first. F of x equals to 7 over 5 plus x, how about minus 2 and plus 2? That's the special version of 0 we did before, but in this case we do it to match the center a equals to 2, which implies we're going to have some x minus 2 to the n power in our series. Alright, so I'm going to group this. So that's 7 over 5 plus x minus 2, that's our u that we will turn into a power series, and let me write just these two outside, plus 2. Combine them together, 5 plus 2, that's a 7. And we are sort of getting there, alright? We already, at least we got the center. At least we got the shifting to get the desired center for the series. Now, there is an issue here. Well, again, the numerator, it doesn't matter what it is. Just multiply it outside if necessary and then put it back in once you get the series. It's this 7 causing trouble here. This 7 right here has to be strictly a 1. How do we get that 7 into a 1? Divide or multiply by 1/7 in both the numerator and in the denominator. That's going to give us the following. Oh, well, in this case, it's going to be a lot of cancellations, which is cool. That's 1 over 1 plus x minus 2 over 7. But we still have some little issue. This plus right here, and that plus has to strictly be a minus. Well,
We can switch to an and factor
factor it out. And does that look like 1 over 1 minus u? I know, that u looks like madness, I know. That's 1 over 1 minus u, where u equals this madness here, negative x minus 2 over 7. And well, 1 over 1 minus u, isn't that just sigma n equals 0 to infinity of u to the n? Let's just do that. U to the n, where u equals negative x minus 2, quantity over 7, and just back substitute for u. Negative x minus 2 over 7 to the n power. Well, we're essentially done with the series in terms of x. Let's just simplify and be careful, because this negative to the n is going to be the alternating factor, x minus 2 to the n over 7 to the n. So do you see all the tricks we had to do before getting just to get the function with the desired shifting, so we can turn that into a power series? So That's again a very typical exam question, so you might want to look into this, and it's also a very common what you call homework question as well. So, this is the end for today.